Think about a moment when you mentally multiply two numbers. You hold one number in mind, hold the other, apply a rule, and store the intermediate result somewhere before combining everything. That kind of fluid juggling of variables is what computer scientists call working memory, and it's something digital computers handle effortlessly through registers and random access memory. But neural networks, for all their pattern recognition prowess, have historically been clumsy at it. This paper from Alex Graves, Greg Wayne, and Ivo Danihelka at Google DeepMind asks a deceptively simple question. What if we gave a neural network its own scratchpad and made the whole thing differentiable so it could learn how to use that scratchpad by gradient descent? The motivation is grounded in a long-standing tension in machine learning. Recurrent neural networks, especially long short-term memory networks, or LSTMs, can in principle simulate any algorithm because they are Turing complete. But in practice, their memory is entangled with their computation. Every piece of information they retain is smeared across the same hidden state vector that's also doing the processing. It's a bit like trying to do long division while only being allowed to remember things by changing your mood. You can do it, sort of, but it doesn't scale. Prior work like LSTM partially addressed this by introducing gated memory cells that act as perfect integrators, meaning a value written into them doesn't decay unless the network explicitly chooses to overwrite it. But even LSTM doesn't have a real addressable memory where you can stash arbitrary values in named locations and retrieve them later. Earlier attempts in the connectionist literature, going back to debates between Fodor, Pylyshyn, and people like Smolensky and Pollock in the 1980s and 1990s, tried to bake variable binding into neural networks through clever encodings like tensor products or holographic representations. These approaches were ingenious but limited, often requiring hand-designed structures rather than learning the binding mechanism from data. What the authors propose instead is to give the network an explicit external memory matrix and let it learn, end-to-end, how to read from and write to that memory. Here's how the Neural Turing machine actually works. You have a controller, which is just a regular neural network, either feed-forward or an LSTM, that takes inputs from the outside world and produces outputs. Alongside it sits a memory matrix, a grid where each row is a vector storing some piece of information. The controller doesn't access this memory directly. Instead, it emits parameters that define so-called read and write heads, conceptually borrowed from Turing's original tape machine. The crucial trick is that these heads don't pick a single location to read or write. Instead, they produce a soft weighting, a probability distribution over all memory locations. A read operation returns a weighted average of all the rows, and a write operation modifies all rows in proportion to their weights. This blurriness is what makes everything differentiable. If the head focuses sharply on one location, you essentially get the discrete behavior of a real Turing machine. But because the operation is fundamentally continuous, you can backpropagate gradients through it. The really interesting design choice is how the weights over memory locations get produced. The authors combine two complementary addressing schemes. The first is content-based addressing. The controller emits a key vector, and the system compares that key to every row in memory using cosine similarity, then applies a softmax sharpened by a learned strength parameter. This is like searching memory by what's in it, a kind of differentiable associative lookup. The second is location-based addressing, which is where things get clever. After content-based addressing produces a weighting, the controller can choose to interpolate it with the previous time step's weighting via a learned gate, then apply a shift, implemented as a circular convolution with a small shift kernel, then sharpen the result with another learned scalar. The shift mechanism lets the network do things like move from one address to the next address, which is what you need to iterate through a sequence. Think of it as the difference between Googling for a phrase versus walking down a row of file cabinets one drawer at a time. You need both. And to keep the focus from getting fuzzy after repeated shifts, the sharpening step exponentiates and renormalizes the weights, pulling probability mass back onto a small number of locations. Rights are decomposed into an erase step and an add step, taking inspiration from LSTM's forget and input gates. The controller emits an erase vector and an add vector, and these modify each memory row in proportion to the write head's weighting. The erase is element-wise multiplicative, and the add is element-wise additive. So the controller has fine-grained control over which dimensions of a memory slot to clear and which to update. The experiments are deliberately algorithmic. The authors test copying, repeat copying, associative recall, dynamic n-gram modeling, and priority sorting. In each case, they compare NTM with a feed-forward controller, NTM with an LSTM controller, and a vanilla LSTM. The results are striking. On the copy task, where the network sees a sequence of random binary vectors followed by a delimiter and must reproduce them, the NTM learns far faster and converges to a much lower loss than LSTM. More importantly, when tested on sequences far longer than anything seen during training, say length 100, when trained on lengths up to 20, NTM continues to copy nearly perfectly, while LSTM falls apart almost immediately past the training horizon. By inspecting the read and write weightings, the authors show that NTM has effectively learned a copy algorithm. It writes each input vector to a successive memory location during the input phase, then walks back through those locations during the output phase. That's genuine algorithmic generalization, not statistical interpolation. Similar stories play out for the other tasks. On associative recall, the NTM learns to compress each multi-vector item into a single memory slot and use content-based lookup, followed by a shift, to retrieve the next item. On dynamic n-grams, it learns to use memory as a counting table that approximates the optimal Bayesian predictor. On priority sort, it learns to map priority values to memory locations linearly, essentially using memory as a sorting array. Now for the limitations, some acknowledged and some not. The tasks here are quite small and synthetic. Memory has just 128 locations, and on the copy task, that becomes the hard cap on generalization because shifts wrap around and overwrite previous data. The repeat copy experiment reveals that NTM can't actually generalize counts beyond its training range because the count is encoded as a scalar input rather than a learned discrete representation. Training is also notably finicky. Gradient clipping at plus or minus 10 is essential, and the softmax-based addressing can be slow to commit to sharp focus early in training. The paper doesn't really test the architecture on natural data like language or images. And one quiet but important point. Even though the memory is external, in the sense of being a separate matrix, every read and write touches every location to some degree, which means the computational cost scales linearly with memory size at every time step. That's fine for 128 slots, but becomes problematic at scale. The broader implication, though, is significant. NTM was an early and influential demonstration that you can give neural networks structured, addressable memory and let them learn to use it as part of standard gradient descent training. It seeded a whole family of follow-up architectures, including the differentiable neural computer and various memory-augmented networks, and the attention mechanisms it pioneered are direct intellectual ancestors of the attention used in modern transformers, where queries, keys, and values play roles very similar to the content-based addressing here. Now, let's walk through some questions you might have after hearing all of this. You might be wondering why the read and write operations have to be blurry across all memory locations rather than picking one slot. The answer is fundamentally about differentiability. If the network made a hard, discrete choice about which location to access, there would be no smooth gradient flowing back to tell it whether a slightly different choice would have been better. By making the access a weighted sum over all locations, you get a continuous function whose gradient tells the controller how to nudge its addressing parameters. The cost is that every memory operation touches everything, but the benefit is end-to-end training with standard gradient descent. A natural follow-up is why the authors bothered with location-based addressing at all, when content-based addressing is in principle more general. The reason is practical learnability. Yes, you could embed location information into the content of each memory slot and use content-based lookup to simulate location-based access, but that would require the network to discover that trick from scratch, which is hard. By providing shift operations as a built-in primitive, the architecture makes iterative algorithms like walking through an array directly expressible, and the experiments show that without this primitive, generalization to longer sequences essentially fails. You might also ask what's actually different between an NTM with an LSTM controller and a standalone LSTM. After all, LSTM already has internal memory cells. The key difference is the separation of computation from storage. In LSTM, the same hidden state vector that does the processing also holds the memory, so they interfere with each other, and storage capacity grows quadratically with hidden size because of the recurrent weight matrix. In NTM, the memory matrix is decoupled from the controller, so you can scale memory independently, and the controller's job becomes learning what to put where rather than juggling everything internally. The experiment suggests this decoupling is what enables the qualitatively better generalization to longer sequences. For large-scale recommendation systems, the ideas in this paper map onto several concrete production challenges. The most direct connection is to user modeling with long behavioral histories. Most production systems compress a user's entire history into a fixed size embedding via a sequence model, which loses fine-grained information about specific past interactions. A memory-augmented approach lets you keep explicit slots for distinctive user actions, like the rare purchase or the unusual genre exploration, and retrieve them by content when a relevant candidate appears at ranking time. The content-based addressing mechanism is essentially the same machinery now used in retrieval-augmented systems and in attention-based two-tower models, where item embeddings act as keys against query representations built from user state. More practically, the lesson that explicit, addressable memory generalizes better than implicit hidden state has direct implications for cold start and few-shot personalization. If a new user provides a handful of signals, you want a model that can write those signals into accessible slots and condition on them at inference, rather than relying on slow gradient updates to a global model. The compromise that production systems usually accept, which is that you don't get full end-to-end differentiable memory because it's too expensive, is exactly the constraint that approximate nearest neighbor indexes and key-value caches address at serving time. The intellectual lineage running from NTM to modern attention to retrieval-augmented ranking is one of the most important threads connecting this 2014 paper to today's recommender stacks.